Pranjali. I'm just reading out your names. I have to get used to your names. Pranjali, okay. Zara. Okay. Bliti. And Miss Jade. Lina. Srishti. And Shreya. You are twins. I could make out by Ashok Yadav. Okay, who is Ishi? And she, Grace. Your Grace. What's your surname like?
Surname or first name?
No, that's Trinity, Grace, and
Chiriyan.
yeah.
Chiriyan.
Okay. Yeah, I know some of the names are. Okay, girls, are we okay till now? Yeah, shall we start? So we have seen how the clock rule actually helps us to find out the polarity. Okay, by looking at the direction of the flow of the current, you can make out whether that particular phase is going to be a south pole or it is going to behave like a north pole. Now, obviously we are talking about a dipole. That means we are coming closer to the fact that when electricity is passed, it is becoming like a magnet. Do you think this magnet is a temporary magnet or it is a permanent magnet? Why do you think it's a temporary magnet?
Because it's only a magnet when electricity.
Correct. It's only going to be, or it's going to behave like a magnet only when you're passing electricity. The moment you switch it off, obviously it knows it is not going to behave like a magnet. Therefore, an electromagnet is a temporary magnet. Okay. Can the strength of the electromagnet be controlled?
Yes.
What are the two methods of controlling the strength of the magnet?
Increasing the charge and increasing the
Number of coils. Very good. So we have seen that by increasing the number of coils, you can increase the strength of the magnetic field. Second thing is also you can increase the current which is flowing through. You can make out that the strength of the magnetic current will also increase. Right? Okay. So we are coming back again to point number 6. We left it halfway through. The magnetic field lines pass through the loop in the same direction. Did you notice in that loop? Okay. The current is also flowing in the same direction. So obviously the magnetic field lines are also in the same direction. They appear to come out from the face of the loop on the other side. So that face behaves like a north pole, while the magnetic field lines appear to enter in it on the front face of the loop. Therefore it behaves like a south pole. Thus the loop behaves like a dipole. Did you understand why it is called now as a dipole? Dono pole hai, north and south. So therefore the loop is behaving like a dipole. Put a tick mark, underline. And it has a magnetic field similar to that of a magnetized disc of radius, same as that of the loop. Okay. Then of course the last part of the paragraph, read it up. You are wrong. Okay, right.
The polarity at the two faces of loop depends on the direction of current in the loop. On reversing the direction of current in the loop, the polarity at the faces of loop gets reversed.
Is that okay? Polarity gets reversed. When does it get reversed? When you are changing the direction of the current. Because the direction of the magnetic field depends upon the direction of the current. The moment we change the direction of the current, obviously it's going to change. Next.
The polarity at the faces of the loop is determined by the clock rule.
And we have also explained what is the clock. Now in your notebook, please take down quickly. What is the last thing I have given you? You have written about the right hand. Okay, now the next heading, magnetic field due to current in a loop. Or you can also write in bracket, or in a circular coil. Okay. Just a few points. I'm sure all of you have marked all the 6 points in your textbook. I'll not be telling everything in detail, just a few key words that you need to use in the answer paper. First point, magnetic field lines. First point, that magnetic field lines are nearly circular. Look at the second point. What does it say? What does it say in second point? Regarding the direction. Okay. So what do you write about the direction? Magnetic field lines are in the same direction. Second point. Magnetic field lines are in the same direction. Third point. What happens in the center of the loop? What is the shape there? Center of the loop, what is happening? It's nearly parallel. It's almost parallel. Right now. Third point. In the center of the loop, the field lines are almost parallel. And in bracket you will write nearly uniform. It's almost uniform in the center. Okay. Then come to the next point. Field lines are along the axis of the loop. Field lines are along the axis of the loop and normal to its plane. Next point, strength can be increased. Strength of what? Magnetic field. You can write NF, just be short, no? Instead of writing magnetic field. Okay? Strength of magnetic field can be increased. What are the 2 points we have discussed? By increasing the number of coils and by, yes, point number A and B, right up. Point number A, by increasing the number of coils Okay, and the second point number B is by increasing the strength of the current. The last point, the loop acts as a dipole. The loop acts as a dipole. That means it has got a north face and a south face. And you are going to use your clock rule for finding out which face. Is that okay? On the same page, there is a clock rule. Do you see that box? Put a tick mark. Okay. I want quickly just draw the diagram so that you know how it has to be, how it is to be used. Write the heading as clock rule. Write the N and the S. Look at the tail of the alphabet. The tail of the alphabet will give you the direction of the current, whether it is anti-clockwise or clockwise. If it is clockwise, which pole?
South
pole. The other one obviously is the north. Done? Got it? Okay. So now we are ready to understand what is a solenoid. Right? So from this experiment itself, we know that you can make a pretty powerful electromagnet by using a simple conducting wire and which has got many coils. So now we are going to find out what is a solenoid. Solenoid is nothing but a simple device where you are having a coil of many turns. Suppose I am taking copper wire, an insulated copper wire. I am taking the wire and on any cylindrical surface, it could be a cardboard, it could be a wooden piece or whatever it is. What am I doing? I am making coils. Okay? Tight coils. 10, 20, 30, maybe 50, 60. What have I done? I am increasing the number of coils. As we are increasing the number of coils, it becomes a very powerful magnet. So what am I doing? This end of the wire, I am connecting it to a positive terminal. This end of the wire, I am connecting it to a negative terminal. In addition, of course, I have to have a switch in order to switch it on, switch it off, or whatever it is. And there's going to be a rheostat, right? Now, can you make out that when I'm passing current through this solenoid will behave like a magnet? Will it behave like a magnet? Yes, because we have already seen that it is having a dipole. One part of it will behave like a north, and the other part of it will behave like a south. How do we know this is north or south? I have to look at the winding here. Okay, if this winding is like this, if it is in the anti-clockwise direction, what will it be?
North.
Okay, then if you look at here, it is going to be in this direction, it is the clockwise direction, therefore it's going to be the south end. Right? The moment I switch off the current, what will happen to the solenoid?
It won't be a magnet.
It is going to be demagnetized. It is no longer going to be a magnet. Okay? Can we increase the strength of this magnet?
Yes.
Yes. You have learned two ways. Instead of having 40, 50 turns, suppose I'm making only 5 turns. What will happen to the strength here? Obviously, it will be less. I'm having the same 1 meter. Let us assume that this is 1 meter. With 1 meter, I'm just making only 5 coils. In the same case, taking the same 1 meter, I'm taking another case where I'm making at least about 50 coils. Did you see that? The length of the wire is the same, but it depends on the number of coils. More the number of coils, what happens to the diameter?
It decreases.
Decreases or increases? One big 5 coils I have made, and on this side I have made many small coils. So come on. Yes, the diameter, you're right. The diameter decreases if you have made a smaller coil. So sometimes you come across this word. As the diameter of the coils decreases, what happens?
The number of coils.
Number of coils are increasing
Charge.
and strength of the strength of the magnetic field increases. So it all depends upon the number of coils. If you are increasing the number of coils, the diameter is becoming smaller and smaller because each coil is becoming smaller. If the coils are becoming smaller, then obviously the strength of the magnetic field increases. Okay? So what is a solenoid? Solenoid is nothing like this. That's all. I've just taken 4 or 5 coils for you to understand. On one part of it, connected to the positive terminal, the other part of it is connected to the negative. You may have one, or you may have 2 or 3, right? Is that a complicated diagram now? Did you understand? Yeah? So what is happening here? Once I have connected, this is a basic diagram. So I'm starting with the basics so that you don't get confused. I've connected it to a cell. The current flows from the positive, this way, coming back here. It depends upon how you are winding it. So if you're looking at it from this end, it is like this. It is clockwise. So it is the south. And when I'm looking at it from this end, the coiling is on the other side. So if this is south, obviously this is the north. Did you get it? Okay. So now, when you're looking at the solenoid and you have been able to make out which is the north and the south, can you also recollect what we are talking about? Bar magnet. Solenoid is very similar to that of a bar magnet. It has got the magnetic lines of force starting from the north going to the south. So this itself, you can imagine that it is behaving like a bar magnet. One part of it is the north, the other part of it is the south, depending upon the coil. So here they have given the coiling. Can you see? Depending upon the coiling, one part of it is behaving like the north pole, and the other part of it is behaving like the south pole. So you have got the magnetic lines of force running through, right? It is running through, that is inside the solenoid. Did you see that these magnetic lines of force are almost parallel? Did you get it? It is almost parallel, right here. And in which direction? The rule is the same. It's always from the north pole to the south pole. So from north, going in this direction, from north, going in this direction. Okay, I've just drawn only one. Is it going to be only one magnetic line of force? There are many. So in the textbook, they have given many. Is it getting more and more complicated? But did you understand how we are going to actually draw? Okay, how did we draw? We have just taken a wire. Do it along with me. Heading is solenoid. I'm asking you to draw the diagram because it is easy for you to remember. How will we do? Take a wire. Imagine that you're actually doing it, then it becomes easy. Take a wire, see here. And you're making many coils. Okay? And you're connecting it to a cell or a battery. Okay? If you want, you may also put a key there. And the key is closed. Obviously, the current is flowing from the positive to the negative. Okay. Depending upon the way you have coiled it, you know that one part of it will behave like the north and the other one behaves like the south. So if it is behaving like a bar magnet, obviously you will be having magnetic lines of force. Yeah, which one? It depends upon whatever the way you are. You know, if at all this is the way, suppose I'm coiling it this way, then obviously it is going to be the south. I've just drawn a rough diagram here. I've drawn it like that. So if it is like this, then obviously it is going to be the south. Right? If you are drawing a coil like this, then it's going to be the north. So okay, let us just change. So depending upon the way you draw it, either this way or that way. So what is happening? North, and you are also having magnetic lines of force coming this way. You have not one, but you have got many of them. Show the direction also. It's from the north to the south. What's happening inside the solenoid? Inside the coils, you see that those magnetic lines of force are almost parallel. Did you get it? Yes? Once again, I have not shown the rheostat, etc. That is to increase or decrease the current. You can either increase the number of cells, or if you have a rheostat, you can also increase the current. Okay? Done? Come to the points which are given below the solenoid. Switch it off. Would it become so dark? It is so dull. So dull. What? Why is it hurting your eyes? Any problem with others? Would you like to worship a little behind? Will that be possible? Are you okay? I think you should have. Is that okay, children? Okay. Now, who would like to read now? Read. It's my talent, so what you read? Ah. You see this from the pattern of magnetic field lines, it is found that below the solenoid. Yeah.
From the pattern of magnetic field lines.
1 minute. All of you are having the Selena textbook or any other textbook? All of you are having that, huh? Right.
The magnetic field lines in the solenoid are clearly stated and parallel to the axis of solenoid. That is, the magnetic field is uniform inside the solenoid.
So these are the key points. What is the important word? What is the important phrase? Magnetic field is uniform. Next.
The magnetic field lines become denser. That is, a strong magnetic field is obtained by increasing current in the solenoid.
How can we increase? By increasing the current.
The magnetic field is increased if the number of turns in the solenoid of given length is increased.
Second point, we can also increase the number of coils. Those are the key words that I want you to remember. Yes.
The magnetic field is also increased if a soft iron rod core is placed along the axis of solenoid. The soft iron increases the strength of magnetic field of the solenoid as soft iron has high magnetic permeability.
Magnetic permeability. Underline the next one.
In
In figure 10.6, the end P at which the direction of current is anti-clockwise behaves as a north pole, while the end Q at which the direction of current is clockwise behaves as a south pole. On reversing the direction of current in the solenoid, the polarities at the ends of solenoid are reversed because the direction of magnetic field has reversed.
Is that okay? Any problem?
I didn't understand.
Fourth point I said I will explain. Permeability, yeah. So I said, how do we actually make a solenoid? I said you can take any cylindrical object and we can wind it. Okay? Now what they have said is, in order to make a better solenoid, a stronger solenoid, what we usually do is take a soft iron piece. Okay? So I assume that this is a soft iron piece, and then when you're winding it around and retaining the soft iron along with those coils, that makes a better solenoid because it has got a greater magnetic permeability. That is what it's saying. Permeability means what? It is allowing these lines of force, magnetic lines of force to flow through. Okay, permeable, it is allowing. Okay, so a soft iron piece is usually used in most of the devices that you are going to see, whether it is a PC motor or a generator, we are always going to be using a soft iron core. Soft iron is nothing but iron which has got a lesser percentage of carbon. Okay, so that it has got a greater permeability to the magnetic lines of force. Is that okay? Right. Are you done with that? Next, we are talking about the similarities between the current carrying solenoid and a bar magnet, which we have already done. What is the similarity between this and this? This has got dipole. This also has got a dipole. What else? What else? Correct. Both of them are behaving like a magnet and both of them are having. Is this, suppose I'm asking you what the differences between a solenoid and a bar magnet? Okay.
That is also a very magnet.
Yes, this is a permanent magnet, this is a temporary magnet. Then, can we change the magnetic field here?
Yes, you can change this.
Yes, we can change the strength of the magnetic field. Here we cannot change. Okay. Then, can this be demagnetized?
Yes.
Yes, this can be demagnetized. This cannot be demagnetized. Okay. Go to the next page. You find a table there. Comparison of an electromagnet with a permanent magnet. Got it? Yeah. Let's see the first point. Electromagnetic. It's made of a soft iron, made of steel. Permanent magnet, of course. We are talking either a natural magnet or maybe it is also a permanent magnet. Second point. Read.
It produces the magnetic field so long as the current flows in its coil. That is, it produces the temporary magnetic field. A permanent magnet, it produces a permanent magnetic field. The magnetic field strength can be changed. The magnetic field strength cannot be changed. The magnetic field of an electromagnet can be made very strong. The magnetic field of a permanent magnet is not so strong. The polarity of an electromagnet can be reversed. The polarity of a permanent magnet cannot be reversed. It can easily be demagnetized by switching off the current. It cannot be easily demagnetized.
Did you get the differences? What is point number 5? Polarity can be reversed. What does it mean?
And not or else outside.
Yes. Okay, by changing this, obviously by changing the direction of the current, you can easily change the north and the south pole. So therefore the polarity can be reversed. Put a tick mark there. We have discussed regarding what are the similarities. We have also seen what are the differences. Is that okay? Come back again to the previous question. So we know that a solenoid is a temporary electromagnet. Characteristic feature is the strength of the magnetic field can be increased. Okay, the moment you switch it off, obviously, switch it off, it's going to be demagnetized. So it is a great advantage to have an electromagnet, especially if you look at the uses. In a scrapyard, we'd like to separate out all the iron pieces, steel pieces, etc. Okay, iron especially. So that is when these huge electromagnets are basically used. Or if you go to a shipping industries, where they have got these huge containers. Have you seen those containers? Very big containers which are transporting stuff, across. So that entire container, which is almost about some 10,000 kilos or even more than that, that can be easily lifted from one place to the other by using an electromagnet, which you cannot do it with a natural magnet or a permanent magnet because those magnets have to be very huge. But if you are using an electromagnet, just by having the flow of current, you can use it as a industrial purposes. Of course, it's a huge advantage. So we have seen those 6 points there. Put a tick mark for similarities. We have put a tick mark for also the dissimilarities.
Now, is there a difference between solenoid and an electromagnet or
It is an electromagnet. A solenoid is only a name and it is an electromagnet. Okay? Yeah, it is an electromagnet, basically. It's a coil of many turns, that is important. So what is a solenoid? It's a coil of many, many turns. Right? Okay, take down this point. Solenoid. What is a solenoid? If a conducting wire is wound in the form of a cylindrical coil, whose diameter is less in comparison to its length, the coil is called a solenoid. Next point you can also write. It looks like a helical spring. Like in the olden days, we had the telephone wires, no? As this, that kind. Did you get it? So the definition is also given here in your textbook. Magnetic field lines due to a solenoid. The first paragraph is telling you about what is a solenoid. Okay, okay till now? Students, okay, fine? So we have finished, completed similarities, we have finished with dissimilarities. Now we are talking about an electromagnet. We are already familiar with this word electromagnet. Okay? A magnetism which is produced when there is a flow of electricity is an electromagnet. So there are different methods of doing it. It's nothing but a repetition of what we have already done. What are the two things that I have given? First one is construction of an I shape or a bar electromagnet. Did you see that? What have we used? We have used a soft iron core like this, and we have taken a coil, and depending upon the coil winding, whether it is like this, okay, like this, okay, imagine it is like this, and finally coming out, or it is this way. You can find out what is the, which face, which end is behaving like a knot in the south. Are you okay with that? So, looking at the clock face rule, we can find that you can easily make an I-shaped magnet. And this magnet is going to be an electromagnet because it becomes a magnet only by passing of the current. Got it? Is that okay? Yeah. Next is interesting because look at the shape of the magnet which we are using in the next figure. What is the shape? Horseshoe. So this is a horseshoe magnet. So when you look at this, the way it is constructed is you have got both these two poles are facing each other. Unlike a bar magnet where you have got the north and the south facing away from each other. What happens in a horseshoe magnet or a U magnet? These two poles are facing each other. Okay? Suppose one is north, assume that this is north and this is the south. Magnetic lines of force are from which? From always from north to south, from here to here, here to here, either which way. Even if I keep it like this, this is the north to south. If I keep it like this, it's north to south. Okay, so in making use of the horseshoe magnet, we are once again looking at the way the coiling has taken place. Look at the figure very carefully. Observe the figure. A horseshoe electromagnet. You have taken that soft iron piece which is in the form of a U. Okay. Let us say you have got the P and the Q. Did you notice the P arm and the Q arm? So you have the P arm and the Q arm. All that we are doing here is taking the wire and coiling it around. So it's being coiled like that. Okay, and from here, when it comes to the Q, is the coiling taking place in the same direction? Notice in the diagram, how is it? It is coiling is there in the opposite direction. So when you come here, the coiling is taking place in the opposite direction. So that's an important feature when you're talking about the horseshoe magnet. Okay, so the coiling basically gives you either the north face or it is giving you the south face. So when you're running current through it, obviously one is behaving like a north and the other one is behaving like a south. Now the construction part of the magnets is not very important. But what is the basic rule? What is the basic principle that we are going to be talking about? Is what is important. Okay. Come back again to electromagnet. Will you read? Well, one of you did. Read. You read. What's your name?
My name is Jane.
Yeah, read.
On which part?
Electromagnet.
A solenoid behaves like a magnet so long as a current passes through it. As the current is switched off, it loses its magnetic behavior. Thus, a current-carrying solenoid is a temporary magnet and is called an electromagnet.
Underline these words. Electromagnet is a temporary magnet.
Its magnetic field is considerably increased by inserting a soft iron core in it. Thus, an electromagnet is a temporary strong magnet made by passing current in a coil wound around a piece of soft iron. It is an artificial magnet.
So we have the words, key words here to remember. It's a temporary magnet, it is an artificial magnet, and it is an electromagnet. Right? Carry on.
An electromagnet can be made in any shape, but usually the following two shapes of electromagnets are in use. First, the I-shaped magnet or the bar magnet, and second is the U-shape of horseshoe magnet. Construction of I-shaped or bar electromagnet.
No need of construction because we have already understood. Okay, so this part will not be asked for you, but only thing is you must know the way it is going. So what are we going to talk about? Uses a bar-shaped electromagnet is commonly used in a relay. They've given a switching device which is a relay. Okay. Same thing, which is becoming the clockwise and anti-clockwise direction. Same thing has been described. On to the next one is U-shaped magnet. What is important here is once again the winding. Okay. I'm reading the paragraph which is given below the diagram. When the current is passed through a winding by closing the P, the end of the arm P becomes the south because the current in this particular case is going to be what? Where does it become south? When it is in the clockwise. And the others will become anti-clockwise, so it's going to be the north. Okay. Thus, we get a very strong magnetic field in the gap between the two poles. Underline that one. We get a very strong magnetic field in the gap between the two poles. Magnetic field lines vanishes as soon as the current is switched off. Therefore, this is also a temporary magnet. It's nothing but a repetition. Now, this is where uses. Look at the uses. different gadgets like your DC motor, generator, electric bell, etc. Okay. Look at the next paragraph there, next heading. How can we increase the magnetic field? We have already done it many times. Okay. Put a tick mark there. Number of turns and by increasing the current. That. Next page, permanent magnet. We have already done. Correct? Because we have already discussed the difference between an electromagnet and a permanent magnet. Right? Now we come to the advantages. Even advantages we already have seen. What is the advantage of an electromagnet over a, okay, let us say a permanent magnet. Here, strength can be increased and it is a temporary magnet. So whenever you don't require it, obviously you can switch it off. And it is very useful for carrying very huge, for transporting very huge masses of objects from one place to the other. Let's look at the points. Point number 1. Produces a strong magnetic field. What are the keywords here? Underline only the keywords, don't underline the entire thing. Strong magnetic field. Second one. What is the keyword here? Did you recognize what is the important point here? Yes, the strength can be changed. What is the third point? Polarity. Polarity can be reversed. So these are the 3 advantages of using an electromagnet over a permanent. Now look at the uses of electromagnetism. Yes, this is very important. Right? First point is I've already told you, for lifting and transporting heavy iron scrap. Okay, girders, plates, especially when it is not coming. Have you seen any construction of a bridge or something of that sort? You need huge columns, no? Those girders are there. How do they transport it? Obviously by using these electromagnets. One is using a crane, but that crane is going to be pretty risky because it can fall down anytime. So it's always better to use an electromagnet. Okay? They have given you used to lift objects as much as 20,000 kilos. Right? Second, for loading the furnace with iron. You have the smelting, when you are preparing iron, converting it into steel and metallurgy. This is where we are going to be using. Third one is for separating the iron pieces from debris. Fourth is from wood, iron pieces from wood. Where do you think this is going to be useful? Yes?
Surgery.
Especially in army. Did you understand? Where the soldiers are constantly exposed to bullet wounds, splinters. Okay? So they need to remove those splinters from the body. Okay? So in surgery, of course, and in scientific research to study the magnetic properties in a magnetic field. And the last one is electric tram, motors, relay, microphones, loud phones, loudspeakers, etc., etc. The last point is important because obviously it's telling you the advantages of using an electromagnet. Any difficulty here? Yeah? Okay, put a tick mark there. Now, we have spoken about a U-shape. Okay, and they have given you a small diagram in the next page. What does it tell us? What are we using? Which gadget is there? The diagram? The bell. Okay. Now let's go back to a simple village school. In a village school, you don't have the bell or whatever it is. What does the peon do? You take a hammer. Okay? It's the same concept for an electric bell. You have a gong and you have a hammer. So the hammer has to strike the gong, go back, come again, strike. This process has to be continued as long as you are pressing the bell. Right? Once again, if you look at the diagram, you will understand that basically there's a gong. Diagram will not be asked, so don't worry. I'm just giving you a fairly fair idea. This is the gong, and there is a small hammer here. So the hammer has to go and strike the gong. Okay, but what makes it move up and down? So obviously here you have got your, okay, the U-shaped magnet. So when you're passing current, this is going to get magnetized, and you find here there is a strip here. So it pulls the strip. So if this strip is moving closer, what happens is the hammer will go and strike the gong. So when it is demagnetized, this strip is pushed back, so the hammer comes back. So this repeated motion of the hammer striking the gong, coming back, striking it, coming back is repeated a number of times. And that is when you are getting the constant bend. Is that okay? So once again, we are talking about the use of an electromagnet here. By passing the current, this becomes magnetized. It's pulling this part closer so that the hammer strikes the gong. For a moment, if it is demagnetized, this part of it moves back because there are springs here. Did you notice there is spring 1 and spring 2? Those are the springs. So the springs are pulling it back. So it's going to pull it back. Once again, it's going to come closer to it. So once it comes closer to it, the hammer is striking the gong. So this repeated motion is the one which is actually making the electric bell work. Is that okay? Now, once again, construction or the working is not necessary, but what is important for us to realize is the effect or the application of an electromagnet by constructing a U-shape, okay, electromagnet, which obviously is a temporary magnet. Is that okay? Clear? Use of electromagnet in an electric bell. Construction. What are the main parts? You have a horseshoe electromagnet. Did you notice the horseshoe electromagnet in the diagram? Second one is a soft iron armature, which is A. So you have a soft iron armature here, this one. There is one armature here. Then we have a hammer, H, and we have the gong, which is the G. And then of course you have a metallic spring strip. So what is the function of the spring strip? Is to draw back the entire armature coil. Okay? So it is going to be pushing up and down. Every time it is getting pushed closer, the hammer comes in, it strikes the gong, and it goes back. Did you get it? Yeah? Right? Working and function will not be asked. Right. Look at the last paragraph. The process of make and break of the circuit goes on, and the hammer strikes the gong repeatedly, so the bell rings as long as the switch K is getting pressed. Is that okay? Yeah. And we have come now to the end of part A. There's a lot to be learned. Was it difficult for you? Comparatively easy, isn't it? Yeah? Yeah, fine. I very strongly suggest that you go through the various examples which are given. In my book, it is page number 237. I don't know what it is. Yeah, just after the bell and all, you have got a series of questions. Okay, do these examples first. Only then you will go to the exercise. Otherwise, you will get confused. Okay? Let me know if the construction is going to be done. It is not going to be asked. I know for sure. Okay, the construction will not be asked. Neither will the working be done. But only the parts of this you may be asked to identify, where you have a spring and you have a bar magnet, which is an electromagnet, the hammer and the gong. That part of it is going to be important. Once again, what is the principle? We are using the principle of an electromagnet. Got it? So we are done with this part. Take down in your notebook. In your notebook. Can I give you some homework? Okay, will you be able to do? Comparison, just take down. Comparison of an electromagnet with permanent magnet. Second, I want you to also write down electric bell, the parts. I'm just trying to show you something because that's what we are going to be doing now. We're talking about the force via okay, let me get it working. Can you see why it is moving on its own? Can you all see? Maybe it's not aligned properly, and you can see that it follows. All that I've done is what? What do you think I'm doing? There's a battery there, and I put 2 pins there, and the circuit is complete. So what do you think? What is this piece here? Copper wire having a number of coils. I've increased the number of coils. And when I'm, let's see with the connections. I've kept a magnet there. So obviously there are 3 magnets to increase the magnetic field. Okay, let me get it working and then we can see. Okay, so basically what happens is you have the wire and make it work. You have the wires, current is flowing through the wire, and I've also placed a magnet below. Okay, so magnetic field is already present around the magnet. What is present around the wire? Because it's already connected, it also has got a magnetic field. So because of the presence of magnetic fields, there will be a repulsion, and that is how the coil actually is supposed to move. You can see, but some alignment mistake, and it is set in motion. So that means there is a force which has been created. Okay? And this is where we talk about Fleming's left hand rule. Okay, we are talking about another concept. Fleming. It is Fleming's left hand rule. So when we know the direction of the current, we know the direction of we remember it as F, B and I. F is the force, which the direction of the force. B is the direction of your magnetic field, and I will be the direction of the current. So in this particular case, I know the direction of the current. I also know the direction, left hand, not the right hand. Left hand. This was what? What was this? This is the right hand thumb rule. Now what are we talking about? This is the left hand Fleming rule. Okay. So always remember FBI. Do we remember? How do we remember FBI? What is FBI? What? Yeah. Then? Yeah. Tell me what is the full form? Correct. It's the Federal Bureau of Investigation. ठीक है ना? So it's easy for us to remember FBI, right? F, starting with the thumb. B is your pointing finger, and the second finger is I. F, B, and I. F is for force. B is the direction of the magnetic field, and I will be the direction of the current. So your F stands for force. So you will find that your motors and other things will be basically working when we are having a coil which is in the presence of a magnet and it is exerting a force. So when it starts moving, that is how it starts the DC motor, which is set in motion. So this is a very simple acronym that you can remember for us to understand. Okay, what is FBI? F is force, BI. Okay. Let me see why my motor is not working. Yeah, you may leave if you want to. Can you see it is moving, but actually it's supposed to make a nice circle. It's up. Yeah, that could be one of the reasons, and also it's so unstable. Okay, you could also try this at home. There. Did you see that? Okay, did you get it? I'll see you next time. When is your next class? Some something, obviously it has to be a sample. Thank you, class. Remind me to show you a couple of things from your next slide. Do you have any other class, no?
Yes.
What next?
Physics, reflection, what's happening in law.
Okay.
उससे पढ़ा नहीं अभी थियोरी है लेकिन हम तो उसके ऊपर न्यूमेरिकल्स होती है कंप्यूटर में हो जाएगा मैंने नहीं एक्चुअली अभी यार अरे हम लोग का फिजिक्स में क्लास में जा रहे हैं
12 बजे
ये वाला चैप्टर 12 बजे क्यों
12 बजे क्यों
ये कोर्स अभी जब वो पढ़ाएगी ना क्या रोटेशन से शुरू करेगी लेंसेज के बाद क्लास टेस्ट शुभा टेस्ट हो गया आपने कौन सा लेंस चैप्टर हुआ अभी लेंस का ही हुआ वो लेंस ये वाला है कॉन्केव कॉन्वेक्स वाला वो दूसरा वाला है सर जो ये स्फीयर है अभी तो किया था स्फीयर शुरू नहीं किया हमने सर तो किया रोटेशन के हम लोग रोटेशन के तो नहीं तो ऐसा स्फीयर का नहीं रचना हां दैट्स बैलेंस प्रिडिक्ट है फिर भी भाई मैंने देखा तो बात
ओके तो
लेकिन सोना बायो भी रहेगी सिर्फ अभी कितना टाइम बचा है 40 marks के होना भाई इधर भी समझना ये तो आजा बेचारे अगर इधर ये क्या होता है अरे मामा का मैग्नेट क्या तू बायो अरे वो you can't even ask me now. I'm taking a bio physics. She said no, you have to wait for 1 hour. Tell ma'am, bro, don't tell me. What do you do? I'm gonna remind you study. I haven't even started you.
टेस्ट लिखना है
Yesterday I didn't. All right.
फिजिक्स